In the previous lecture, we had started talking about the two-dimensional problem, where we had obtained the weak formulation for a given partial differential equation which arises in the two-dimensional case, and we had considered the generalized problem of heat conduction, steady state heat conduction, and from there we went ahead and used all the tools which we had developed for the one-dimensional problem to obtain the variational formulation for the 2D problem. And we saw what are the major differences between the one-dimensional problem and the two-dimensional problem. And let me recap again. The major differences are that here we are talking of a two-dimensional domain. So the geometry of the domain now plays a role, and how well do we resolve the geometry of the domain is another issue that has to be handled. Okay. For example, I mesh my domain with triangles. This is my domain. I know that these triangles with straight edges will only approximate this boundary curve. Okay. So I have to ensure that this approximation of the boundary curve is decent. That is, I have a sufficiently refined mesh, that is this sufficiently large number of small triangles at the boundary so that these curves are taken care of. We will also see other approaches of exactly representing these curves, these boundary curves, wherever it's possible. So the geometry was a problem, and this leads to the discretization error as far as the definition of the geometry is concerned. Okay. Next thing was that application of the boundary conditions. In the 1D case, we had talked about the boundaries being 2 points, the end points of the domain. Here the boundary could be a line or a curve or a contour. So the boundary conditions have to be now imposed on a contour, on a closed contour. So this is another difference between the one-dimensional and two-dimensional cases. Another thing is we had discussed is that if I have a domain like this, then you see that because of this corner here, corner in the domain, here there is going to be a singularity in the solution that you obtain. Irrespective of what the loading is, I am going to get, depending on the boundary condition on these two edges, I am going to get a singularity in the solution that I obtain in the vicinity of the corner. So these are certain things we have to keep in mind. Now let us go ahead and build the finite element approximation for the model problem we have taken. Okay. And for the sake of simplicity, here I am going to consider the simplified version of that model problem, that is del to u del x squared minus del to u del y squared is equal to r, which is the what we know as the Poisson equation. I have deliberately chosen, with respect to our earlier model problem, a11 is equal to 1, a22 is equal to 1, and a12 is equal to 0. Okay, this is just to fix ideas. Everything else will follow. Okay, we'll take a rectangular domain. In the rectangular domain, we had said we are going to make a mesh of triangles. This is the simplest possible domain that I can have. Let us say it's a square domain, not even a rectangular domain. It's a square domain with sides A and A. Okay, and I have made these triangles. So what we had said is the first thing that we are going to do is construct the crudest possible approximation, and the crudest possible approximation was an extension of the linear approximation that we had in the one-dimensional case. So we would now like to create a linear approximation in the two-dimensional case. The linear approximation in the two-dimensional case would be of this form now. So the linear in the 2D case will be a0 plus a1x plus a2y. And in this linear approximation, what we are going to do is we are going to construct the basis functions over these elements that we have over this domain, such that I have a piecewise linear approximation in each element, like we had in the 1D case. So over each element here, I would like to construct a piecewise linear approximation. The piecewise linear approximation means that over the element, my basis functions, the truncation of the basis functions, are linear polynomials. Now, how many independent functions do we need in an element in order to completely define a piecewise linear? The answer is that since this piecewise linear incorporates 3 unknowns, we need 3 independent functions. In the 2D case, we required 2 independent functions in an element. Now we need 3 independent functions. How do we define these 3 independent functions? We had said that we are going to define these 3 independent functions with respect to the 3 corner vertices of the element, or the 3 corner nodes of the element. These are the nodes of the element of interest. So in the 2D case, I have the triangles as the elements. The corners of the triangles are the nodes. So we are going to define these piecewise linears with respect to these elements. So let us now go and see how we do this job. So what we say is that let the polynomial, let any function u be represented by a linear in the element of interest. So my element could be this guy. And as we have said, that these are the corner vertices of the element. So this is my element tau. I give it some name. Okay. So what we want, as we had done in the 1D case, I want to interpolate the given function u with a linear in this element. So in order to interpolate this function u with a linear in this element, what we do is we say fine, u is given by some linear, which is c1 plus c2x plus c3y in this element. Then we say fine, what is the value of this linear at these nodes of the element? So the nodes of the element have coordinates x1, y1, x2, y2 and x3, y3. So we want a representation of the solution, the function that we have taken at these nodes. So the value of the function at these nodes is u at x1, y1, u at x2, y2, u at x3, y3. And what we want now, by what we have done, similar to what we had done in the 1D case, we want our linear interpolation of this function to match the value of this function at the 3 nodes. So when we have this linear interpolation, we want c1 plus c2 x1 plus c3 y1 to be equal to the value of the function at the point x1, y1. Similarly, I want c1 plus c2 x2 plus c3 y3 to be the value of the function at the point x2, y2 and at the third point. And these values of the function at these 3 points I am going to call as u1, u2 and u3. Okay. So this gives me now, so I assume that I know my function uxy. So given that function, I know the values u1, u2, u3, which can be written in terms of the coordinates of the 3 points and these unknown constants. We want to find these unknown constants c1, c2 and c3. So my u, the 3 values of the u is given as a combination of these unknown constants c1, c2, c3. Now the job is simple. It's a 3 by 3 matrix, this one 3 by 3. So we have to invert this matrix to get c1, c2, c3 in terms of u1, u2, u3. That's about all we have to do. So what we end up getting is, I call this matrix as matrix A. So A inverse will be 1 by twice the area of the triangle, we have called it tau, okay, into this some coefficients alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3, okay, and we can write the area of the triangle A tau in terms of these alpha 1, alpha 2, alpha 3. That's okay. So let's now, what do we get then? The C, the constants, unknown constant C become as A inverse into this vector U, and after expanding this out, the constant C1 is 1 by 2 area of the element tau into alpha 1 U1. U1 is the value of the function U at the first node, which has coordinates x1, y1, plus alpha 2 U2 plus alpha 3 U3. Similarly, I can find C2 and I can find C3, where these alpha i's are given like this in terms of the 3 nodal coordinates. That is, alpha 1 will be x2 y3 minus x3 y2, where I, j, k are written in a cyclic permutation. Okay. Similarly, alpha 2 will be equal to x3 y1 minus x1 y3, and so on. Similarly, I can find what is beta 1 and I can find what is beta I and what is gamma I in terms of the x1, x2, x3, y1, y2, y3. So once I have these quantities, then I can rewrite the linear interpolation of U over the element tau in terms of the values of the function at the 3 points U1, U2, U3 as 1 by twice area of the element tau into alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3 plus the part multiplying x plus the part multiplying y. So this you can say is the part multiplying 1, the part multiplying x, the part multiplying y. So what is the next thing? We would like to group all the coefficients or all the monomials multiplying U1 together, all the monomials multiplying U2 together, all the monomials multiplying U3 together, and rewrite my U in the element tau in terms of the values of the function at the 3 nodes into some polynomial psi I. Psi I is, for us, the psi I tau is equivalent to our, what we know as our element shape function Ni tau. Okay, and it turns out that this guy psi I tau is given as 1 by area of the triangle into alpha I tau plus beta I tau x plus gamma I tau y. Okay, so these are our psi I taus are our shape functions in the element. And how many do we have? We have 3 of them. So we have the 3 linear shape functions in the element are obtained by doing this procedure. Okay, so and you see that it is each of these shape functions is a linear, showing that this set is a complete set, that is, it can represent any linear polynomial exactly by taking a linear combination of these, and showing that these are linearly independent is now a relatively easy job. One can do exactly the same thing that we had done in the 2-dimensional case. So now let us go further. So what will these functions look like? So let me just take an example. Let's say this is node 1, this is node 2 of the element, this is node 3 of the element. So here I would like to plot the function psi or n1. So if I take n1, as you will see, the n1 has a value 1 at the node 1. So what we have, you will see the n1 tau at x1 tau y1 tau is equal to 1. So it will have a value 1 at the first node, and it will have a value 0 at the second node and the third node. So this function is going to be like this. So it is like a slanting roof, okay, and it has a value 1 at the first node, 0 at the other two nodes. That is, it is, you can say, 0 along this whole line. Okay. Similarly, this is my function n1 tau, or what I have written as psi1 tau in the previous slide. Similarly, if I want to draw n2 tau will be a function which has value 1 at the second node and value 0 at the first node and the third node. So this is my function n2 tau. So it is a roof slanting down from the second node. And similarly, I can draw the third function. So these are our element shape functions. And you can see that these shape functions for the ith node, if I look at the shape function, it will correspond to a tent-like structure. Okay, that is, by piecing together all these shape functions, I get the global basis function phi I for the ith node of the mesh that we have, and this function vanishes on these edges. So it vanishes on these black edges, and it is one at the node with respect to which it is defined, and it is piecewise linear in each of the elements which shares that node. You see, remember again that in the two-dimensional case, a node may be shared by many more than two elements. In this figure that I have drawn, there are 4 elements sharing a node. So this basis function has to be defined with respect to all the elements which share that particular node. So okay, armed with this, now we have obtained our representation of the shape functions, the linear shape functions. So let us now go and construct the finite element solution, if I have to do that, in an element. Okay, so I define the finite element solution globally. So given these phi's, let me go and again make a mesh for our own convenience. Let's take an example of a mesh of 8 elements. Simplest possible things we can do. So let's say this is my node 1, this is my node 2. So I am doing a numbering of the nodes in the mesh: node 3, node 4, node 5, node 6, node 7, node 8, node 9. Similarly, I will number the elements. This is element 1, this is element 2, element 3, element 4, element 5, 6, 7 and 8. So I have numbered the nodes, I have numbered the elements. So now I will have how many basis functions formed by piecing together these piecewise linears? I will have 9 basis functions corresponding to the 9 nodes of the mesh. Okay. So now the global, if I want to make a finite element solution which is a linear approximation over this domain, then my UFE would be equal to sum of I is equal to 1 to 9 UI phi I, which is a function of x and y. Okay. Now if I want to look at the restriction or the part of this finite element solution over some generic element. So let's say I am looking at it over this element, third element. Okay. So my UFE over a generic element tau will be given in terms of the value of these coefficients ui at the 3 nodes which are the end vertices of this particular element, okay, multiplied by the restriction of these basis functions over this element. So it will be, I will be writing it as sigma I is equal to 1 to 3 ui in the element tau ni tau. Okay, and what do we mean by this? We understand that if I am in the third element, okay, for the third element I will have a local numbering for the nodes. That is, remember that in the 1D case also we had defined the global numbers and the local numbers. So this could be my local 1, let me put some other numbering. This will be my local 1 node, local 2 node, and this would be my local 3 node for the element. Okay, then I see that the u1 of the element tau is equivalent to the global u2. u2 of the element tau is equivalent to the global u3. u3 of the element tau, which is the third element, is equivalent to the global u6. So for every element I have to obtain the local to global numbering. So remember that same data structures have to be continued here. Local to global enumeration has to be done. Which tells me which global degree of freedom does my local degree of freedom correspond to. Okay. Similarly, the ni taus, the n1 tau for this element is equivalent to the phi 2 in this element, n2 tau is equivalent to the phi 3 in this element, n3 tau is equivalent to the phi 6 in this element. Okay. So we know this one-to-one correspondence between what is the global solution and what is it that we are doing locally. Okay, so once I have the representation of the finite element solution in the element, then I can go and do the next step, that is I can do my element calculations. So for the element calculations, what do we do? If you remember the weak form that we obtained, if I take the weak form and put it for this, for the particular model problem that we have taken, the weak form would be del u del x del v del x plus del u del y del v del y dA would be equal to integral over the domain RV dA plus, if you remember we had talked about the Neumann part of the boundary, the part where the flux conditions are specified, you will get GV ds. G is the specified boundary flux and V is our test function or the weight function that we have used. So this is going to be our weak form, which is obtained as a specialization of the general weak form we had obtained earlier. Okay. Now what do we know about this? What had we done? This we can now partition as sum over all the elements, 1 to number of elements, integral over the element tau of del u del x del v del x plus del u del y del v del y dA. Similarly for the right hand side we can do. Now here from the finite element point of view we replace u with UFE. Okay. Now UFE on the element is given by UFE tau. Similarly, what do we do as far as the V is concerned? We take V to be the global basis functions themselves. Okay, so V would be again given as V over tau. Okay, so here we are talking of which global basis functions which are going to be non-zero in this element are the global basis functions which correspond to the Ni tau, that is the shape functions of the element. So essentially what happens is, as far as the contribution of the element is concerned, the element is going to only contribute to the rows in the global stiffness matrix or in the global equations which correspond to the phi i's which are non-zero in the element. That is, let us go back to our previous figure. If I am in element 3, then corresponding to the UFE that we have constructed, I will have a 9 by 9 global system in terms of the 9 unknown UIs. So, as far as element 3 is concerned, phi 2, phi 3 and phi 6 are non-zero in element 3. All other phi i's are 0. So, my element 3 is only going to contribute to the global equations corresponding to the phi 2, phi 3 and phi 6. That is, it is going to contribute to the second, third and the sixth global equation. Similarly for the other equations. Which rows? It is also going to contribute to the second row, to the third row and the sixth row, because these are the only coefficients or again the basis functions which are active in this element. Okay. So with that understanding, what we need, if I again go back, if I look at it here, for the element there are only 3 active basis functions. Even the UFE of the element is in terms of these 3 coefficients. So the element stiffness matrix will be a 3 by 3 stiffness matrix as far as the piecewise linear approximation is concerned. Okay. So this 3 by 3 stiffness matrix for the element is what we would like to obtain. Once I obtain this 3 by 3 stiffness matrix, then we do the usual process of assembly to get my global system. So what do these 3 by 3 stiffness matrix correspond to? So just like we have done earlier, so let's talk of the integral over the element del UFE over the element tau del x del. Now here instead of the V, we are taking the basis functions which are non-zero in this element, which are nothing but del Ni in the element tau plus del UFE in the element tau del y del Ni in the element tau del y. These are essentially, so corresponding to I equal to 1, 2, 3. We will get the 3 equations from the element. Okay. In the 3 equations, when I substitute for the UFE tau, I will get the 3 columns which are there in terms of the U1 tau, U2 tau and U3 tau. So, okay, now if I do this, I will get the stiffness matrix entry in the element tau by expanding UFE tau is given as integral over tau del Nj tau del x del Ni tau del x plus del Nj tau del y del Ni tau del y. So this is going to be my ijth term of the element stiffness matrix, where I comma j is equal to 1, 2 and 3. So everything that we are doing is exactly the way we had done it for the 1D case. Only thing is the number of entries increases. Here we are dealing with partial derivatives of the quantities of interest. Okay. If I have to do this for the standard model problem that we had taken, the generalized one, then we'll have to do it with the A11, A12 and A22 sitting there. So the element, the stiffness matrix entries for the element can now be computed in terms of the derivatives of the element shape functions Ni and Nj. Okay, where the Ni and J have been obtained from our interpolation that we have done earlier. Okay, so now if I take the piecewise linears, what do we see? We see that these derivatives are going to be constant. So as far as the piecewise linears are concerned and the model problem that we have taken, the integrand here is going to be a constant integrand. This constant we can easily obtain corresponding to each of the I and the J. The integral of the constant against the area will be equal to the area times this constant. So as far as this part is concerned, finding the integral is not difficult at all. One can do it very easily and explicitly. However, let us go and build some of the other features which are going to be important from the point of view of a computational implementation. Okay, so let us first talk of the geometry representation. The geometry, what we are going to do is, the geometry is going to be represented by the x being given in terms, that is in an element, in the interior of an element tau. If I want to find any point x, it will be given in terms of the coordinates of the endpoints of the element. So it will be given in terms of x1 tau as a linear interpolation, again n1 tau plus x2 tau n2 tau plus x3 tau n3 tau. Similarly, y is equal to y1 tau n1 tau plus y2 tau n2 tau plus y3 tau n3 tau. Now if you remember that it was, from a computational point of view, it was much easier to work not in the physical element. We could do everything in the physical element, but we decided to map our physical domain, physical element in the 1D case, to a master element. Similarly, in the case of this two-dimensional problem, let us map our physical element into a master element. So okay, so let's define a mapping. And how are we mapping? It's a linear map. So what happens? I have my physical element, which has these nodes x1 tau, y1 tau, x2 tau, y2 tau and x3 tau, y3 tau. This we are going to map to a master element given in terms of the coordinate system psi eta and defined as this. Our master element is going to be such that the first node has coordinates 0, 0. So the nodes of the master element, I am numbering them with hat. The second node has coordinate 1, 0. Third node has coordinate 0, 1. So what have I done? I have simply mapped my original physical triangle linearly to this master triangle. That is, the straight edges go to straight edges and the area maps linearly. Okay. So I have done this linear map. Now my next job is to define this map. So how do I define this map? So in order to define this map, let us take the linear shape functions and map them to the shape functions that we have, the corresponding entities over the master element. So this master element, I'll call it as tau hat. This is my element tau. Okay. So how do I do this mapping? So since a linear polynomial in the physical element goes to a linear polynomial because of this linear map in the master element, so we had, if a shape function, which is a linear shape function, was 1 at a physical node, it will be also 1 at the corresponding master node. If it was 0 at a physical node, it will be 0 at the corresponding master node, and so on. So if I have the n1 tau, the n1 tau in the master element will become n1 hat. This n1 hat will be a function of psi and eta. Okay. So this is my physical, this is, remember that this is my master. So now what is this n1 as a function of psi and eta? So n1 hat as a function of psi and eta, it's quite easy to show that this is a function which is 1 here and 0 along this line, because you remember that n1 tau was 0 along this line. So similarly n1 hat has to be 0 along this line. This line has an equation psi plus eta equal to 1. So if it is 0 along this line, the function has to be 1 minus psi minus eta. Check this, that this will be 1 at this point because psi eta is 0 and 0 along these 2 points 2 and 3. So this is how I have defined my n1 hat. Similarly, I can define n2 hat as a function of psi and eta is equal to psi. Again, the function which has a value 1 at the second point and value 0 at the first and the third point. Okay. So this becomes psi, one can check. Similarly, n3 hat as a function of psi and eta will be equal to eta. So what happens now, by doing this mapping, I have, at least in principle, constructed the corresponding mapped versions of the shape functions. So how can I define the geometry mapping? Geometry mapping becomes x is equal to x1 of tau into n1 hat plus x2 of tau into n2 hat plus x3 of tau into n3 hat, and y becomes y1 of tau into n1 hat plus y2 of tau into n2 hat plus y3 of tau n3 hat. So this is how I can give the x and y at any point psi and eta in the master element. So the corresponding value of x and y. So once I have done this mapping, now remember that we want to do our master calculations. So in the master element, you remember that we had an integral of this type. Nj tau del y dA. We would like to convert it to an integral over the master element. So from the physical, I come to the master, where I have the integral over the master element tau hat of this integrand, okay, this integrand converted into a expression in terms of sin eta into now the area in the physical element has to be mapped to the area in the master element So that will be in terms of something called the Jacobian into dA hat. The question is, what is this guy, and how do I map these derivatives to get, that is, how do I use the derivatives in the master element to obtain the derivatives in the physical element. So for that we will have to obtain the matrix of the transformation. Okay, so how do we obtain the matrix of the transformation? So if I say that I want dx will be equal to del x, because x is now a function of sin eta, del x del psi d psi plus del x del eta d eta. Similarly, dy is equal to del y del psi d psi plus del y del eta d eta. This is because x and y are functions of sin eta. So change in x is given in terms of change in sin eta. Now we have to obtain these quantities. Where are these quantities going to come from? These are going to come from the definitions of x and y that we have given in terms of the three nodal x and y's in the physical element and the definition of the shape functions in the master elements. Okay, so one can show from that expression that we have there that del x del psi is equal to x2 of tau minus x1 of tau. Okay, let us go back and see. Here, if you remember, n1 tau, n1 hat was 1 minus psi minus eta. n2 hat is psi, n3 hat is eta. So if I take this definition and go back, dx d psi will be equal to x2 minus x1. Okay. Similarly, del x del eta is equal to x3 tau minus x1 tau, and del y del psi is y2 tau minus y1 tau. Del y del eta is equal to y3 tau minus y1 tau. So let us now rearrange this thing in a matrix form, whatever we have written. So I can write it as dx dy is equal to del x del psi del x del eta del y del psi del y del eta d psi d eta. I have simply rewritten this expression in a matrix form. So once I have this expression in the matrix form, then I can talk of the Jacobian. The Jacobian is nothing but the determinant of this expression, of this matrix that we have written. Okay, and we would like to obtain, for, as we'll show, for whatever we have to do, expressions for del psi del x, del psi del y, del eta del x, del eta del y. That is, we can, since we can write x and y in terms of sin eta, we can also write sin eta in terms of x and y. So you want the matrix of the inverse transformation. So how do I do it? By exactly following what we have done there, we can get d psi d eta is equal to del psi del x del psi del y del eta del x del eta del y dx dy, and this matrix is nothing but the inverse of what I will call as the Jacobian matrix here. Why inverse? You take the inverse of this guy, bring it on this side, you will get d psi d eta in terms of dx dy. So all we have to do is, given this matrix J, we need to find the inverse of that matrix. Now the inverse of this matrix J, so this is equal to, we'll say J inverse. Okay, so what is going to be the inverse of this matrix? So J inverse is equal to 1 by Jacobian. We interchange the diagonal entries, so I'll get del y del eta del x del psi, and take the negative of the signs of the off diagonal entries. So minus del x del eta minus del y del psi. So this is my J inverse, and the J inverse is now going to give me my del psi del x and so on. So del psi del x is equal to 1 by Jacobian into del y del eta. Del psi del y is equal to minus 1 by Jacobian into del x del eta, and del eta del x is going to be minus 1 by Jacobian into del y del psi, and similarly del eta del y is equal to 1 by Jacobian into del x del psi. So I obtain the matrix of the inverse transformation. Why do I need it? Because I need to obtain, if you remember, these quantities, which is equivalent to saying as del ni hat del psi del x plus del ni hat del eta del x, right? Because I can rewrite my ni tau in terms of ni as a function of sin eta, that is ni hat as a function of sin eta. Then the x derivative of ni tau is given by this chain rule, that del ni del psi del x del ni del eta del x. These quantities now we need to obtain. But these quantities are quite easy because we have already obtained each one of these quantities, okay, from the definition of the x and y. So given these quantities, I can go ahead and now define what is my del psi del x del eta del x. In this case, you notice that for these triangles, linear mapping, this del psi del x, del y del eta, del x del eta, del y del psi, del x del psi are all constants. Why? Because x and y was linear in terms of sin eta. Take the derivative of the linear, you will get constant. Because they are all constant, the Jacobian is also a constant. This is true only for the linear maps of triangles. Okay, we'll see that when we go to quadrilaterals, the Jacobian will no longer be a constant. Okay, so again let me see what we have here. Okay, so given these entities, now we can plug them in and obtain all the quantities. So for the element, I have to input the three nodal coordinates, the x1, x2, x3, y1, y2, y3 for the element, and I can construct the matrix of the transformation. Okay, so let's take now a simple example, a very simple example of again the same domain that we had taken. Let's assume that my elements have edges of size h. Okay, so given these elements of size h, I would like to construct, let's say, for the first element in my domain, the entries of the stiffness matrix using the linear approximation. So in the next class, what we are going to do in the next lecture, we are going to construct the elements of the stiffness matrix of the element. Then we'll talk a little bit about the assembly for this special problem. Another important thing that we are going to talk about in the next class is, in passing, how to apply the natural boundary conditions, that is the force boundary conditions, and we will also finally discuss how to apply the displacement boundary conditions. Okay, once we do that, then we are not going to be happy with linear approximations in an element, so we would like to extend it to higher order approximations, quadratic, cubic, fourth order, and we'll see how we can construct the basis functions or the shape functions in an element corresponding to any order of approximation that we desire, and then how to put it in the framework of whatever we have developed here as far as the element calculations are concerned.